Hello, everybody, and welcome to week 10 of Math 4400. So last week, we started looking at squares modulo p, and we introduced the Legendre symbol, and we sort of explored its properties, which gave us an effective way to compute whether a number n was a square modulo a prime p. And so to get there, we just collected some data, then we made some observations, we looked at some patterns, and we wrote down the properties of this Legendre symbol, but we didn't justify those properties. So the main topic of this week is to explain how you can actually sort of mathematically, rigorously justify that these properties of the Legendre symbol hold. Okay, and so the first thing we want to do to see that is to give a nice concrete formula for the Legendre symbol. So just to recall the definition, so the Legendre symbol was defined, so Legendre symbol of n over p is just 1 if n is a square mod p, and -1 if n is not a square mod p. We defined this for Thursday last week. And so the formula is going to be as follows. So p is an odd prime, and then n is anything not divisible by p, just like in the definition of the Legendre symbol. Then it turns out the Legendre symbol of n over p is just actually equal to n to the p minus 1 over 2 mod p. So I'll explain in a second. In a second, we'll see why this is always plus or minus 1 mod p. But okay, so this gives you a way to compute the Legendre symbol by just raising n to some power modulo p. And we've already seen in raising the powers is also a pretty simple thing to do because you can use like the method of successive squaring to compute powers. So this is a pretty powerful statement. But this is also a statement we can use to deduce properties of the Legendre symbol. So before I prove this, I'm just going to do some examples and then deduce some properties, and then we'll come back and we'll sort of explain why this formula is true. Okay, so well, for example, let's just check this formula is true when p is equal to 7. So in that case, we've checked before, and you can check again that the non-zero squares are 1, 2, and 4. So that means the Legendre symbol is given by 1. It has values 1 for n 1, 2, and 4, and has values -1 for 3, 5, and 6, which are the non-squares. Okay, so that's Legendre symbol. Let's just check we get the same thing when we do n cubed. Well, so if I do 1 cubed mod 7, that's 1. If I do 2 cubed mod 7, that's 8, which is again 1 mod 7. If I do 3 cubed, well, that's 27, which is 3 times 7 plus 6. So this is 6 mod 7, but 6 mod 7 is just -1. So I get a -1 there. And then, well, you could keep on going. 4 cubed is 64. That's 63 plus 1. So this is 1. 5 cubed is 125. Now I'm sort of starting to get pretty high. But you could keep on doing these out on your own, and you'd get indeed you get -1 here and -1. Another thing you can do is you can use the same trick. So we always use when we're filling out these tables. So if you notice, like this goes 1, 1, -1, and then it sort of repeats 1, -1, -1. So this repeats, but sort of times -1. So we sort of flop the signs and repeat it going backwards. Like when we do this kind of table, sort of with n squared, what we got was like we sort of this part, and then it just repeated backwards. Well, here when we do n cubed, like minus n cubed. So yeah, this is a useful note. Minus n cubed is just minus n, or yeah, minus n cubed. It's -1 cubed is -1. So you can use that to sort of see that the second part of this table will just sort of fill in the minus sign, the minus way. Of course, if and this really depends on sort of p being 7 here, because 7 and sort of this 3 is 7 minus 1 over 2. So for example, if I took p to be, let's say 13 instead, then I would sort of be taking the 6th power, and I would so then I would really just repeat this pattern, whatever pattern I got up to p minus 1 over 2 without a minus sign, because sort of -1 to the 6 is 1. Of course, it's also related to the rule for the Legendre symbol for -1 over p. Okay, but anyway, well, at least in this example, these two formulas agree. Good. Let's continue assuming the formula holds, and let's see how you can get some of the properties of the Legendre symbol from it. So for example, we get multiplicativity, because if the formula holds, then a Legendre symbol of a over p is just a to the p minus 1 over 2 times b to the p minus 1 over 2, which is just a times b to the p minus 1 over 2. So this is just using this basic property of multiplying powers, so you can sort of just pull them together. So if we know that this gives you a formula for a Legendre symbol, then the fact that Legendre symbol is multiplicative is just sort of the fact that powers are multiplicative. Okay, so that's simple. We also get that -1 to the p, or sorry, the Legendre symbol -1 over p is 1 if p is congruent to 1 mod 4, and -1 if p is congruent to 3 mod 4. So why? Well, if p is congruent to 1 mod 4, well, that means p is equal to sort of 4 times some number k plus 1. So then -1 to the p minus 1 over 2 equal to -1 to the 4k plus 1 minus, so it's 4k over 2, which is -1 to 2k, which is -1 to an even power, so that's 1. Okay, whereas if p is congruent to 3 mod 4, then p is equal to 4k plus 3 for some integer k. So then -1 to the p minus 1 over 2, that's equal to -1 to the 4k plus 2 over 2, which is -1 to the 2k plus 1 now, which is -1, because this number is odd, because the exponent is odd. Okay, so again, we just very quickly get this formula we very quickly get this condition for when -1 is a square mod p, if we know this formula that we can compute it as a power. Okay, so now let's go over the justification for why that holds, why that formula holds, the proof of the theorem. Okay, so starting here, the proof of the theorem. So we're trying to prove this formula holds. Well, let me look at it again. I mean, one thing that's implicit in this statement is that, in particular, n to the p minus 1 over 2 has to be +1 or -1. So let's explain that first. Well, if I take n to the p minus 1 over 2, and I square that, well, I just using the rules of powers and squaring, so this 2 pulls in and multiplies the exponent. So I just get n to the p minus 1. And that's 1 mod p by Lagrange's theorem. So if I take anything in fp cross and raise it to the p minus first power, I get 1. This is what Lagrange's theorem tells us. But because of that, that means n to the p minus 1 over 2, it's something whose square is equal to 1. And so it has to be 1 or -1. I mean, these are the only roots of x squared. So only solutions of x squared is equal to 1. It's the same. They're roots of x squared minus 1. So here, so we're secretly using, well, at least one way to think about it is we're secretly using this statement that a polynomial has at most, a polynomial of degree d has at most 2 d roots. So here, this degree 2 polynomial has 2 roots, and we know 1 and -1 are both roots, so that's sort of all of the roots we can have. So that means if you have some root, in this case n to the p minus 1 over 2, it has to be one of those two. Okay. So good. We've at least checked that sort of these two functions have the same range. So we know the Legendre symbol sort of takes values plus or minus 1, and now we know this n to the p minus 1 over 2 that this takes values plus or minus 1. And because of that, all we need to show now is that n to the p minus 1 over 2 is congruent to 1 mod p if and only if n is a square mod p. I mean, somehow, because if this is not true, then now we know, so if not, the point is we only have one other option for both sides. So since we know n to the p minus 1 over 2 is either 1 or minus 1, well, if it's not 1, that has to be minus 1. And if n is not a square mod p, if n is a square mod p, not a square mod p, then, sorry, if n is, right, the only option, other option to n being a square mod p is n is not a square mod p. Okay, so it suffices to show just this first statement. So n to the p minus 1 over 2 is congruent to 1 mod p if and only if n is a square mod p. Okay, so how are we going to do that? Well, we're going to use the discrete logarithm. So let's set that up. So this is something we talked about on Tuesday of week 7. So if you're a little bit rusty, you might go back and look at that. But what we do is we choose a primitive root g for fp. And then corresponding to that, we get this primitive this discrete logarithm function I that sort of takes an element in fp cross and spits out something in z mod p minus 1z. And it's sort of defined by the property that I of g to the k is equal to k. So it sort of it undoes raising g to powers. So for example, I think this is an example we've computed before, but let me just write it down here. When p is equal to 7, I can take my primitive root to be 3, and then I sort of just write down the powers, and I then sort of reverse it, doing this kind of table we've done before, and I get this table that computes I. So when n is 1, 2, 3, 4, 5, 6, I of n is 0, 2, 1, 4, 5, 3. And this really just says sort of 3 to the thing on the bottom is the thing on the top. So I is the inverse function to sort of g to a power. Okay, good. And let me highlight insert the thing in the top. This is an F7 cross. So when p is 7, this row on the bottom, these are all sort of, you should think of these as being elements of z mod 6z. It's sort of the powers, again, this was by Legrange's theorem, that sort of the powers of g only depend on k mod p minus 1. Okay, so we're going to use this discrete logarithm function in order to justify this statement that n to the p minus 1 over 2 is congruent to 1 mod p if and only if n is a square mod p. Okay, so the first step is to use it to show that n is a square mod p if and only if I of n is even. So just in our example, well, when n, let me highlight the squares here. So the squares were 1, 2, and 4. And indeed, whenever n was a square, I of n was even. We got 0, 2, and 4. And whenever n was not a square, so 3, 5, and 6, then I of n was so not a square mod 7, so I of n was odd. Okay, so that checks out, at least in this example. I mean, let me highlight, it makes sense to say I of n is even, even though I of n is not an integer. Like I of n is something in z mod p minus 1z. But it still makes sense to talk about it being even or odd, exactly because sort of the thing you're looking modulo, this p minus 1, is also even. So this makes sense. Let me just write that, and this makes sense because 2 divides p minus 1. So somehow that because of that, two numbers that are congruent mod p minus 1 are also congruent mod 2. So it makes sense still to talk about even or odd modulo p minus 1. And of course, then you can sort of see that if you look like in this example, like mod 60, of course, like it makes like, I don't know, like 3 is congruent to 9 mod 6, but 3 and 9 are both odd. And you can't get something that's congruent. Two things are congruent mod 6 where one's even and one's odd. That's okay. So somehow this sentence I of n is even makes sense. Okay. Good. So let's justify. We saw it holds an example, but let's actually sort of justify it. So, well, if n is a square mod p, then we can write n is equal to x squared for something in fp. And if n is equal to x squared, then just applying the discrete logarithm, we get I of n is equal to 2. Okay, is equal to I of x squared, which is 2 times I of x. So that's obviously even because multiplied some by 2. On the other hand, if I of x is even, then we can write, or sorry, I of n is even, sorry. If I of n is even, we can write I of n is equal to 2 times I of y, or sorry, 2 times y. But then that means, so if I raise both sides to, if I sort of take both sides to be the exponent of g, so I get sort of g to the I of n, which is just n, is equal to g to the 2y, which is g to the y squared. So n is a square. So that's all that's going on. And somehow this divisibility by 2 for the discrete logarithm just comes from the fact that sort of when you have a square, then you pull down that 2. Okay, good. Maybe I should write this n that appeared this equation here. This was n because this is g to the I of n is equal to n. Okay, so good. So we have that n is a square mod p, if and only if I of n is even. Now I need to sort of connect this to this condition I'm interested in, and I want really what I want is sort of I wanted to show that n to the p minus 1 over 2 is congruent to 1 mod p, if and only if n is a square mod p. So now I just have to show that n to the p minus 1 over 2 is congruent to 1 mod p, if and only if I of n is even. Okay, but this is good because, well, if I of n is even, then p to the minus 1 over 2 times I of n is going to be congruent to 0 mod p minus 1. So it's going to be equal to 0 and p minus 1 and z mod p minus 1z. And really that's sort of if and only if. I mean, somehow if I of n is even, that means you can write as 2 times something else. And so that 2 will cancel this 2 in the denominator, and you just get p minus 1 times something. And of course, that's 0 in z mod p minus 1z. Good. So this is an equivalent statement. But now, okay, and I guess sort of I should have justified, I mean, so I didn't really tell you why p minus, like if this holds, then sort of I of n has to be even, but it's not so hard to see. No, so maybe I leave that as an exercise. I mean, certainly we see that like when we look at this example. Like the things you multiply by 3 to get 0 are exactly the even ones. And I think I even left it. I made a table here, so I should scroll down. Like in this example, I of n was 0, 2, 1, 4, 5, and 3. And exactly like if I multiply I of n by 3, I get 0 for all of the even things. So like 3 times 0 is 0, 3 times 2 is 6, which is 0 mod 6, 3 times 4 is 12, which is 0 mod 6. And then I got something non-zero for all the odd things. So 3 times 1 is 3 mod 6, that's not 0. 3 times 5 is 3 mod 6. 3 times 3 is, so 3 times 5 is 15, so that's 3 mod 6. 3 times 3 is 9, so 6 plus 3, that's 3 mod 6, and so on. So somehow being even is the same as sort of 3 times it being 0 here, and that holds sort of in general. I'll sort of let you think about that if you want to justify that statement any further. But once I have this first line, then, well, p minus 1 over 2 times I of n, that's the same as just taking the discrete logarithm of n to the p minus 1 over 2. And that's what the discrete logarithm does. It sort of turns multiplication into addition, so it sort of turns exponents into multiplication. Good. But I mean, that means n to the p minus 1 over 2, so by the definition of the discrete logarithm, is equal to g to the 0, which is equal to 1. Okay, so in the end, I get the statement I wanted. Yeah, I n of n is even if and only if n to the p minus 1 over 2 is equal to 1. And then because I already had n as a square mod p, if and only if I then is even, together I get sort of n as a square mod p, if and only if n to the p minus 1 over 2 is equal to 1, which is exactly what I was left to show. Okay, so we've gone ahead and we've now finished the proof of this theorem that says for p and odd prime, I can compute a Legendre symbol by computing n to the p minus 1 over 2 modulo p. So, right, we've established that theorem. And then before we even established that formula, before we sort of went through that proof, we saw that as a consequence, we got the multiplicativity of the Legendre symbol and the formula for the Legendre symbol of minus 1 over p. So we already saw that these two were consequences once we knew that formula. So we've established those. There are still a few properties left from last week that we've not yet established. So that's what we're going to do with the rest of the week. So the other two things we needed, the other two properties we talked about last week were when is 2 a squared mod p? So what is the Legendre symbol of 2 over p? And it was 1 if p is 1 or 7 mod 8, and minus 1 if p is 3 or 5 mod 8. So we observed that that seemed to hold, and I told you that holds. But we never actually sort of gave any mathematical justification that this holds. So we still have to do that. And similarly, so we have this quadratic reciprocity rule for the Legendre symbol of p over q is equal to the Legendre symbol of q over p if either p or q is congruent to 1 mod 4, or minus the Legendre symbol of q over p if both p and q are congruent to 3 mod 4. So again, sort of this is something we observed. I told you it was true, but we haven't actually sort of given any real justification for it. And so that's sort of what we have left to understand this week. And the way you do this is a little bit surprising, at least the first time you see it. I mean, maybe always. But there are many proofs of these rules, but somehow what it boils down to is you want to express square roots in terms of something else. You want to express square roots using roots of unity. So these are sort of roots of. So roots of unity is something that's a root of the equation x to n minus 1, whereas a square root, like this, is a root of x squared minus d. So something you want to express roots of a polynomial that looks like x squared minus d in terms of roots of polynomials that look like x to the n minus 1. And it's sort of totally not obvious that you can do it, but it will become much more believable once we see some examples. So that's what we're going to do mostly in class on Tuesday with the worksheet. And then we're not going to actually meet in person on Thursday. So there will be no sort of in-person or Zoom session on Thursday, but there will be a slightly longer video posted where we'll go through then the rest of the justification for these formulas. Okay, so I'll see you in class on Tuesday. Thanks, everybody.